Today, I'm figuring out what it would take to build a light bulb out of algae. Hey, I'm Olion, and I'm once again experimenting with microalgae. Last week, I officially started brainstorming for what's gonna be my final project in my basement lab. And I came up with a whole bunch of ideas. So this week, I want to start going through some of them and start either killing ideas or moving them to a further research stage. And to do this, I'm going to be engaging in essentially what I'm calling idea sprints. Basically what I want to do is take an idea and quickly validate any of the assumptions that are associated with it and figure out what would need to be done for me to execute that idea. And then that way I can decide what ideas to kill and what ideas to keep moving forward with. And today's idea is my bioluminescent algae light bulb. Now, this idea for an algae light bulb actually came from an AI. I plugged some parameters into ChatGPT and asked it to come up with some ideas for my final project. And one of the coolest things they came up with was this idea for an algae light bulb. Basically taking algae that are bioluminescent, in other words, they produce their own light through a series of chemical or biological reactions, and making that into a light bulb that could, say, be used to light up my room. So my main question for this idea sprint is this possible? And the key question is, how much algae would I need to replicate the brightness of a typical 60-watt light bulb? You know, the sort that you might screw into your ceiling. So I started doing some research, and I found out that the most common bioluminescent algae, the one that is used in most experiments, is Noctiluca scintillans. It's a dinoflagellate which consumes some phytoplankton and then uses a chemical called luciferase to essentially produce the light that it produces. Now it produces blue-green light at around 480 nanometer wavelengths. Now what we want to do is convert that photon value along with the wavelength to the energy released by that 1 microliter of N scintillans. So what we're going to do is take Planck's constant times the speed of light and divide it by the wavelength, which as I mentioned is 480 nanometers. And what we get is that each photon produced by N scintillans has an energy of 4.14 times 10 to the negative 19 joules. Now, assuming that it's released over 1 second, this comes out to 4.14 times 10 to the negative 19 watts, with essentially a measure of just how much energy is emitted per second. So for the 2 trillion photons emitted by each microliter of the culture, this comes out to 8.68 times 10 to the negative 7 watts. Now, that's not a lot of energy. But remember that this is also just 1 microliter of solution. That's 1/1,000,000th of a liter. So let's keep carrying this forward. And actually, this is where it gets a little more complicated. Because now we have to figure out how to convert from watts, which is a measure essentially of power, to how much we see, which is more so a measure of brightness or luminous intensity. And what that measure is in the unit of lumens, which is essentially a measure of how bright something is to our own eyes, to a human eye. Now, there's something called the luminous efficiency graph, which is on screen right now. And essentially what it does is it converts the wattage to a number in lumens according to how our human eye perceives that light. So in the case of 480 nanometers, for a light that is 480 nanometers in wavelength, it is about 90 lumens per watt. For every watt of energy, or watt of power rather, at 480 nanometers, you get out 90 lumens of brightness to the human eye. So multiplying that out, we get a value of 0.0000745 lumens per microliter of culture. Now, we want to replicate the brightness of a 60-watt light bulb, which has 800 lumens of brightness. So dividing those two numbers, we get how many microliters we need, and we can divide that by 1,000,000 to get that we need 10.74 liters of N scintillans culture to replicate a light bulb. Now, that is just a starting estimate, and it's based on the assumption that there are about 50,000 cells per milliliter, which sounds like a lot, but is reasonably common for culture sizes like this. And it may not be that difficult to get something in the range of 10 to the 5 cells per milliliter. But still, that said, it might require up to 20 liters or so of actual culture just because the culture density ends up being lower. But even then, I could see myself putting 20 liters of N scintillans culture inside a big jar and calling that a light bulb. So I'm going to give this idea a check mark stamp of approval. So there we go. I've come up with one idea for my potential final project in my basement lab, an algae-powered light bulb. And if you think this is a good idea, let me know down in the comments below. Now, I'm going to be running more idea sprints like this over the next couple weeks. I think the next one on my list is giving my algae-powered micro battery, so make sure you stay tuned for that. So as always, make sure to follow on LinkedIn, subscribe on YouTube, and as always, I'll see you in the next one.